Welcome to Beyond Biology Lab YouTube channel. Today, we're exploring the rigorous transition from traditional diagnostic limitations to what is rapidly becoming computationally augmented oncology. For decades, our ability to detect cellular anomalies has been strictly bound by the biological limits of human vision, not to mention the physical constraints of our clinical workflows. But as complex deep learning architectures begin to converge with medical imaging and histopathology, we're witnessing a fundamental shift in exactly how we decode the very earliest signs of disease.
In this explainer, we'll be moving through a quick syllabus to understand this shift. We'll start with the early detection challenge, look at how biology meets computation, dive into specific workflows for breast, lung, and colon diagnostics, and finally, wrap up with the realities of clinical integration.
So let's jump right into part one, the early detection challenge, focusing on the biological problem and our current diagnostic limitations.
To really ground the stakes of our discussion today, consider the 2022 GlobalCan estimates. We saw approximately 9.7 million individuals globally succumb to cancer. In the US alone, we anticipate over 609,000 fatalities annually. The overarching challenge across all disciplines of oncology is that early-stage cellular mutations are incredibly subtle. They just blend right into the surrounding healthy tissue until the disease progresses to a much more lethal, systemic stage. And when we rely purely on traditional screening, we hit a wall with severe resource constraints and an unavoidable degree of human diagnostic variability. For instance, early lung cancer screening using traditional CT scans requires a pretty significant radiation exposure, around 7 millisieverts. On the flip side, computational augmentation optimizes these entire workflows. We're talking about a massive reduction in workload, enhanced precision, and consistent pattern recognition that simply doesn't suffer from cognitive fatigue at the end of a long shift. That brings us to Section 2, Convergence. Biology meets computation, specifically looking at deep learning and convolutional neural networks.
What you're seeing here is the rigorous journey from medical dataset collection straight through pre-processing into hybrid AI fine-tuning. It's important to understand that convolutional neural networks don't just look at a tumor. They map medical datasets by extracting pixel-level features. Through intensity normalization and image patch adjustments, these models isolate structural patterns, the shapes, the edges, the microtextures that are fundamentally invisible to the naked eye, and they abstract them into sequence vector features for purely computational evaluation.
And the empirical outcomes from these pipelines are highly significant. Look at recent studies on multi-cancer image classification. Models like DenseNet 121, which utilizes densely connected blocks where every single layer receives input from all the preceding layers, achieved a validation accuracy of 99.94%. That's alongside a root mean square error of just 0.045 on histopathology datasets. This signifies a level of high-fidelity pattern recognition we just haven't had before, distinguishing incredibly subtle tissue variations across multiple cancer types.
Let's see how this applies in practice in Section 3, Augmenting Breast Cancer Diagnostics.
We are seeing specific architectures yield highly targeted results here. Take the CADx system. By leveraging vision transformer self-attention mechanisms, it analyzes mammograms in literally fractions of a second. We're talking 0.048 seconds, while achieving over 97% binary accuracy. Other deep learning systems are showing high precision in identifying invasive ductal carcinoma, and models like CADe use a combination of feature extraction techniques like SIFT and HOG to categorize breast masses based on complex geometries. Ultimately, these models do a fantastic job of balancing sensitivity and specificity, and that is absolutely vital if we want to prevent unnecessary biopsies and all the patient anxiety that comes with them.
Moving on to Section 4, let's look at lung and colon workflows, expanding this precision to the respiratory and gastrointestinal systems.
These models are proving incredibly versatile. For lung cancer, AI networks like 3D Dense Sharp are vastly improving the segmentation and characterization of early-stage lung nodules. By predicting invasive labeling and segmenting lesions much more objectively than a standard radiological consensus might, the AI effectively mitigates the subjective, human variations that have historically led to missed diagnoses.
And this directly translates to better patient outcomes. The shift to low-dose CT scans drops radiation exposure from 7 down to just 1.6 millisieverts, which suddenly makes broad screening highly viable. And the stakes couldn't be higher here. Detecting lung cancer early improves the 5-year survival rate from a dismal 5.2% to over 57%. In parallel, AI-assisted colonoscopies are enabling real-time optical diagnosis of polyps, optimizing adenoma detection right there during live procedures. Plus, we're tracking some fascinating emerging research exploring liquid biopsies using mRNA-seq enzymes to detect both lung and colon cancer from simple blood samples.
But obviously, this isn't without its hurdles. That brings us to Section 5, Clinical Integration and Ethics.
It's absolutely crucial to ground our expectations in the reality of this technology. Real breakthroughs have already entered preclinical testing, but the clinical consensus across the board is clear. AI is amplifying scientists, not replacing them. The computational heavy lifting, the pixel-level feature extraction we talked about, is handled by the machine. But high-level clinical decision-making, contextualizing a diagnosis within a patient's unique history, and of course patient empathy, those remain entirely the domain of human doctors.
To actually realize this collaborative future, ethical and policy challenges will shape the future implementation of these technologies. We have to standardize vast, fragmented medical datasets. We must rigorously address data bias so these models can generalize safely across diverse global populations. We also need to establish deep clinical trust, which requires transparency in how these models process information. And finally, widespread adoption is going to depend entirely on long-term, prospective, multi-center studies to prove these tools actually reduce cancer-related mortality over time.
Let's wrap up with Section 6. A new era begins. As we examine the current evidence, it is clear that this is just the beginning of a new era in biology and medicine. So we really must ask ourselves, what does biology become when computation decodes its most complex errors? By looking past all the hype and focusing purely on the evidence, we actually find a deeply hopeful trajectory for oncology. We are moving toward a future where engineered life systems and raw data converge, creating a medical infrastructure intelligent enough to catch biological errors long before they become life-threatening. If you're interested in where science is heading and want to stay updated on future explainers like this, make sure to follow along, where science meets tomorrow. Thanks for watching. Please like and subscribe Beyond Biology Lab YouTube channel.